The setup of this question is pretty clear. We have two boxes pictured here at one instant in time and here at an earlier instant in time. A collision happened somewhere in there, and the masses of these two boxes are 3 kilograms and 4 kilograms, as they are here and here. We're given the velocity of the first box here and the second box here, but we're only given the velocity of the box mass 3 kilograms here and not the velocity of the box mass 4 kilograms. So there's two goals to this question. First of all, it's to figure out the velocity of this box here, and secondly, to answer whether this collision is elastic. And if I haven't made it obvious already, that's what I'm aiming for here, but we've got to prove that it's elastic. So elastic, prove it. In order to find this velocity, we're going to need to know a few other values. We're going to need to know the momentum there. We're going to need to know the momentum of this box here, the net momentum here, and the net momentum here. Then, to figure out whether the collision is elastic, we're going to need to know the kinetic energy of both these boxes here, as well as the kinetic energy of both these boxes here, and the net kinetic energy. So even though we're only being asked two very simple questions, what is the velocity of this box and is the collision elastic, there are quite a few values we're trying to figure out. So let's push forward with them now. Finding this velocity. We're going to use the fact that momentum is conserved in this collision here. So the net momentum over here is the same as here. So the net momentum here is made up of the sum of this momentum and this momentum. P is equal to mv, that's 3 times 5 here, or 15. P is equal to mv, that's 4 times 2, that's 8. So the net momentum is equal to 23 kilograms times meters per second. That is the same as the net momentum here. So 23 kilograms times meters per second. We can also figure out the momentum of this box here. P is equal to mv, that's 3 times 1.57, or 4.71 kilograms times meters per second. Since the net momentum is 23 and this box contributes 4.71 kilograms times meters per second, the momentum of this block over here must contribute the rest. So the momentum of this block is equal to 23 take away 4.71, which is equal to 18.29 kilograms times meters per second. And if we divide 18.29 by the mass of this block, since that is equal to mv and the mass is 4 and the velocity is a mystery, if we divide this number by 4, we'll get v by itself. So the velocity is 18.29 divided by 4, or around about 4.57 meters per second. There we go, we're halfway done. Let's pause for a moment and ask ourselves, since we'd rather not continue on with an incorrect answer, is that velocity sensible? This block here is moving at 5 meters a second. If that is the positive direction, sorry, I should have specified that. If that is the positive direction, this block is moving quite quickly and this block quite slowly. So this block here, when it crashes into the block in front, like a bumper car, when you crash into someone who's in front of you, even if they're moving, you will still slow down. And we see that this block goes from 5 meters a second to 1.57 meters per second. Meanwhile, If you are in front of someone in a bumper car and they slam into the back of you, you would expect to be accelerated forwards. And this block experiences that. It was moving at 2 meters a second, and now it's moving at 4.57 meters per second. One other good sign is that this block is not moving more quickly than this block had been. That would be quite strange if this block started moving at more than 5 meters a second. But it hasn't, and it has accelerated from 2 meters a second, so I'm quite happy with that answer there. Now we can test to see if this collision really is elastic. The blocks haven't stuck together, so that's a positive sign. It's not definitive, but if they did stick together, we would expect an inelastic collision. Let's start to work out the kinetic energy. The kinetic energy of this block here is 1/2 times m times v squared. So that's 0.5 times 3 times 5 squared, or 37.5 joules. Always work in meters, a second, and kilograms. The kinetic energy of this block is 0.5 times 4 times 2 squared, which is 8 joules. So the combined kinetic energy of these two blocks is equal to 37.5 plus 8, which comes to 45.5 joules exactly, worth of kinetic energy. If we find that the blocks over here have the same amount of kinetic energy in total as they do here, the collision will have been elastic. So the kinetic energy of this block is 1/2 times 3 times 4.7, times 1.57 squared, which I have coming to 3.70 joules. And the kinetic energy of this block we expect to be actually quite a lot higher. High velocities tend to push the kinetic energy up quite a bit. The kinetic energy here is equal to 1/2 times 4 times 4.57 squared, which comes to, I have around about 41.77 joules. If we add both of these together, 41.77 plus 3.70, we get a total of, depending on the approximation you've used, I have 45 point, no, I'll use the approximation first. So 41, see the reason we may have different answers here is because I like to carry the values through on my calculator. So even though I wrote down here 41.77 joules for the examiner, on the calculator I had 41.7698. Now that answer is not actually accurate because it's based on another approximation, but instead of trying to re-enter a bunch of digits into my calculator, I'll just hit enter and bring that down. So I'm actually now going to add 41.77. I'm doing not the way I usually do now. I'm actually entering new digits. So 41.77 plus 3.70 comes to 45.47 joules. Whereas if I just carried my figures through, so 3.69735 plus 41.7698, I had 45.4672. So that could be more accurate. I'm happy with this answer though, because what I find is, that's terrible math there. What I'm trying to say is that the net kinetic energy over here is equal to 3.70 plus 41.77, which is equal to 45.47 joules. That is incredibly close to 45.5 joules. In fact, it's close enough that I can assume the kinetic energy has stayed the same, and the only thing I've done wrong is started using some approximations in here where I should have kept exact values. So since the kinetic energy here is so close to the kinetic energy here, I can say that since EK initial is equal to EK final, the collision is elastic.